Hello, WeatherTech students. Today we're going to talk about a topic that is near and dear to my heart. I enjoy lecturing on it, and so we'll jump here into atmospheric stabilities. And for this class, we're going to spend a notable amount of time expanding on the concepts learned in MET 103 and starting to work our way into understanding the skew-T log P thermodynamic diagram. And so on the screen you can see the join code for Stepanek's lecture. If you are in Gobert's lecture, 393390 will get you to his slides. And so as we start our presentation here, you can see stability and soundings. And so refreshing our idea of what do we mean when we talk about atmospheric stability. And so when we talk about atmospheric stability, we're really looking at this vertical profile of the atmosphere and trying to determine based upon temperature and moisture how the atmosphere is going to behave and what we might expect from phenomena such as clouds and the like. And so here we can envision our red rubber ball and what would happen if we pushed it in a certain direction. And so in the stable environment, a little nudge to the left or right is simply going to see the ball return to its original state. Whereas in the unstable environment, a little nudge either way is going to have it continue to move in that direction. And so stable is the idea that if something is pushed upward in the environment, it's simply going to return back to its original level. And in unstable, a little push upward is going to result in additional upward motion. And then the neutral type environment, where if I pushed it left or right a little bit, it would simply stay in that location. And this is where, again, when we think about the atmosphere, we started to work in other types of stability, things such as conditionally unstable. Times where, depending on whether or not we consider the moisture available in the environment, we may see a different type of rising motion. And this is going to be one of those things where looking at both temperature and dew point in tandem become very important when we're trying to understand what the potential is for, say, severe thunderstorms to occur in the afternoon hours. And again, we could go back to this idea of lapse rates. And so this goes back to the overall concept of parcel theory. And parcel theory is kind of that little basketball or volleyball sized parcel of air. It is a, to be fair, fictitious idea, but it allows us to idealize and better understand the processes that work within the atmosphere. And so again, we have to also remember that rising motion is going to potentially lead to cloud development, and depending on whether or not we have rising motion in a stable environment or in an unstable environment may mean the difference between some stratus or sheet-like clouds in a stable environment versus our puffy cumulonimbus type clouds in an unstable environment. And so when we have these parcels rise, remember first and foremost that any rising parcel is going to cool. That is it. It will cool. The question is, at what rate will it actually cool? And so here we have our two lapse rates, our dry adiabatic lapse rate, which here is shown as 10 degrees Celsius per kilometer. We can also look at it at 9.8 Kelvin per kilometer. There are ways to break it down into Fahrenheit per 1,000 feet, but that is reserved more for topics such as aviation. And then we have our moist adiabatic lapse rate, the Maller. Sometimes we'll see it called the Waller, the wet adiabatic lapse rate, or even the Saller, the saturated adiabatic lapse rate. And unlike the dry adiabatic lapse rate, which is a constant, the moist adiabatic lapse rate is going to vary. Remember, though, that when we talk about a dry adiabatic lapse rate, we're referring to a parcel that is unsaturated. Simply put, it has less than 100% relative humidity. The moist adiabatic lapse rate is what occurs once the parcel reaches saturation. And so I strongly encourage you to read a portion of your handout this week on Chapter 2 entitled Why is the Waller Lower Than the Daller? It's kind of fun to talk about them as acronyms, but this is all going to be related to the moisture content. The idea that this is not actually an adiabatic process, the idea that we are going to have to do some conversion of water vapor, and as we do this conversion, this latent energy release helps to offset the rate of cooling. And so you're going to have to give that a little bit of thought as we move forward. But let's step forward into what is, well, relatively new here in MET 130, and that's the idea of the thermodynamic diagram. And so we have three here on this slide. The skew t log p, usually just referred to as a skew t because skew t log p is just so much more to have to say. We also have a couple other here, the stuvie, the tephigram, and one that's not mentioned here but is also a thermodynamic diagram, the emagram. And so the stuvie is the first one that we're just going to show a quick example of. You do not need to become an expert in the stuvie, and you will not need to become an expert at any point in your undergraduate career. The stuvie is relatively simplistic, and if your knee-jerk reaction is, oof, that's simplistic, I understand. But you can notice that most of the lines are straight in nature. You can also see that there's at least some relationships that you can probably glean looking at the lines, and there are valuable aspects to this stuvie, but it does lack some energy and area equivalence, which means that it is actually not commonly used within meteorology. The tephigram, okay, now we're starting to look a little more complicated here. The tephigram has actually a lot of similarities to what we're going to discuss shortly with the skew t log p diagram. The one thing about the tephigram is that it is actually used somewhat commonly in certain parts of Europe, and in corners of Canada would be another place that we will see the tephigram used. But Britain, Ireland, a couple areas over there do regularly use the tephigram. And again, this is a perfectly suitable diagram when we start to look at that energy area equivalence. And it doesn't make a lot of sense what I mean by that now, but this is going to start to dovetail into quantities or parameters such as CAPE, which I'm guessing most of you have heard of and we'll talk about in the subsequent lecture. And so here's the skew t or skew t log p diagram. And this is what you will become very familiar with as you work your way through your meteorological curriculum here at Valparaiso University. And unless you step far outside the confines of any type of forecasting or weather prediction, is something you will certainly use as you move into your actual meteorological career. And so although it does take some time to understand and master, we'll give you the baseline for that here in this lecture, talk about some of the parameters and levels that we can glean from plotting a skew t, and your homework this week is going to work, not surprisingly, with dealing with skew t log p diagrams within Python. And so when we look at these diagrams, as I've already alluded to, the skew t log p is going to be the one that is most commonly used. And so we are going to focus on that. Energy conservation is a critical component to a good thermodynamic diagram. And if for some reason you feel like you want to be the one student from this class who masters the tephigram, I will say more power to you, and it is something that will not be completely useless in your career moving forward, and you will likely be able to show off at whatever office you work at down the road. And so let's take a little bit of time here at the end of this lecture series to talk about the skew t and all of these different lines. And so a blank copy of the skew t is provided on the Blackboard page for this week. I encourage you, if able, to make a copy of that, and we'll talk about one of the tasks that is in your handout this week that, although not required because it is a task, is something I do encourage you to do. You will have the opportunity to plot skew t diagrams in subsequent classes here at Valparaiso, and getting a chance to just feel out how this works is something that within this virtual learning environment may be a very good use of your time. And so let's try to deconstruct this skew t. We're going to talk about this, and then I'm going to bring in an interactive one that should help to hammer it home a little bit. And that will be what is in the link here on the left side of your screen. And so this drawing or this schematic is from this weather prediction URL listed at the bottom of your slide. And let's talk for a moment about many of the different lines on this. Looking at your y-axis first and foremost, we can see that we have pressures that are ranging from 1,000 millibars up through 100 millibars. You may note first that they are horizontal, and they may be colored brown in most of your colorized images. But the other thing that should jump out at you is the fact that they are not separated by equal distance. They are much closer packed down here near the surface than they are as you go higher and higher in the atmosphere. This is why we refer to it as a log P diagram, because it is based off the logarithm of pressure. It's important because as we plot data that comes back to us from radiosondes, we're going to look for temperature and dew point at various pressure levels. And so when we dot points and connect some of these features together, we're going to be doing that in a way that is reliant on what pressure the measurement is being taken at. The second thing that I'll point out here are these isotherms. These isotherms are going to slant from the lower left corner of your diagram towards the upper right, or some might say from the southwest to the northeast. And these are going to be your isotherms in degrees Celsius. And so you can see here values such as -40, getting warmer as you work your way to the right side of the diagram. And so hopefully not often are you going to have to deal with temperatures greater than 40 degrees Celsius. Yes, that is 104 Fahrenheit. And hopefully you're not dealing with many temperatures, at least near the surface, of less than -40 Celsius, which you hopefully know is also -40 Fahrenheit. But the big thing here is that these isotherms are slanted or skewed. This is why we refer to it as a skew T. It is a skew of temperature logarithm of pressure type diagram. And so these are going to be equal distances along that x-axis, and we're really going to focus on plotting values along some of these isotherms when we look at our temperatures. There's going to be some other lines that are slanted here, but are a little difficult to see from the lower left to the upper right, and these are going to be dashed and typically in green, and these are going to be lines of constant mixing ratio. Constant mixing ratio lines are going to become important as we try to determine additional values related to moisture in trying to figure out what's going on in our atmosphere. We have other lines that are going to be here called dry adiabats. And these are going to go from the lower right corner to the upper left corner, and unlike our isotherms, these are going to have some type of curvature to them, and that is based upon this logarithm of pressure. And so the idea here is that we are cooling at that dry adiabatic lapse rate, and these are going to be then that near that 9.8 degrees Celsius per kilometer. Finally, we have other lines here that are from kind of the lower right to the upper left. And these are going to be curved green lines that are moist adiabats. And so moist adiabats, another term for that would be the constant equivalent potential temperature lines. And these are going to become critical again as we start to figure out some other parameters that are on our skew-T diagram. And so a number of these other features here, these solid lines, are an example of an environmental sounding with temperature and dew point, and then what might be determined through some of our analysis to be the parcel lapse rate. And so what I'm going to do now is pull in an additional web page here. This is the additional link that is on this slide. And what we're going to do here for a moment is we're going to look at some of the different lines here as we break it down. And so this is the skew-T, which you might look at in a colorized sense. And so when we break it down, we have our temperature lines or our isotherm lines. These are the ones, again, from the lower left to the upper right, separated here in single degree intervals with some bolder lines occurring at intervals of 5 and 10 degrees. Pressure, again, these are going to be our horizontal lines, skew of temperature, log of pressure, becoming more widely spaced as we go higher up in the atmosphere. Our dry adiabats, when we pull these out, you can see that again, relatively diagonal, but there is a little bit of curvature as you go higher and higher up in the atmosphere. They're going to lie relatively, or I should say almost perpendicular to your isotherms, and these are going to be those lines of constant potential temperature, typically referred to as dry adiabats. Your moist adiabats are much more strongly curved, and you can note that that curvature increases as you get higher and higher in the atmosphere. And so your moist adiabats are going to be one of those parameters, again, related to what is the amount of moisture that can be held at a given temperature, your Clausius-Clapeyron relationship. Clicking on mixing ratio, These are going to be green, or here bluish dashed lines with values down along the x-axis. Again, you can note that your mixing ratio lines have much higher values as you get over here towards these warmer temperatures on your SKU-T than you do in these much colder temperatures. Again, related to the idea that you can only hold so much moisture if the temperatures are very cold in the atmosphere. And finally, although we haven't gotten into great detail, we typically will plot our winds on the right side of our SKU-T diagram, and the winds become very important when we're looking at certain features in the atmosphere. And so take a little bit of time and read what's on page 4 of your handout. The idea that we're going to look at temperature and dew point as I toggle back to our slides here. We're going to look at temperature and dew point relative to pressure, plot those out, and look for certain features here. Maybe we have some strong inversions that are occurring in areas where it's warming near the lower levels of the atmosphere, potentially caused by radiative cooling in the overnight hours, maybe a subsidence type inversion. We may also look for areas once we get high up in the atmosphere where the temperature starts to warm with height. This idea of what's known as a negative lapse rate, or temperatures increasing, and maybe this is where we're getting up into the stratosphere, where ozone is helping to cause warmer temperatures due to that absorption of UV radiation. And so we also will look at dew point, which may be quite variable as you go up in the atmosphere, areas where it may be close to saturation. Other areas here, for instance, in this example, around 500 millibars, we have a very low dew point with, well, cold, but still much warmer temperatures. And so we would be very unlikely to find clouds when these temperature and dew point are separated by such significant distance. But finally, let's talk about here the wind speed that's going on. Here we have a relatively unidirectional profile. We have some surface temperatures here, or surface winds I should say, from the southwest, turning to more of a west-southwesterly direction. You can note that they increase with height. We have what looks to be about 10 knots down here near the surface, increasing to about 50 knots as you get up towards 500 millibars, and continuing to increase as you get up higher in the troposphere and into the lower stratosphere. Again, friction is often going to keep our winds a little lighter near the surface, but we are going to be very interested in looking at certain things such as veering of winds, where the winds are turning clockwise with height, so a southerly working its way to more of a westerly direction as you move up in the atmosphere. Backing winds, which are indicative of cold air advection, are going to be when our winds are turning counterclockwise with height. And so we oftentimes focus on things such as veering winds in the low levels of the atmosphere when we're looking for the right shear profiles that are going to be conducive towards severe weather. Okay, and so why do we use the thermodynamic diagram? It's going to allow us to analyze the stability of the atmosphere, help us to capture lapse rates in the atmosphere, help us to get an overall picture of certain threats, whether it be severe weather or whether it be a mixed precipitation type event. Lots of different things, and it's simply put one of those things that the more SKU-Ts you take the time to look at and really try to understand even the most basic aspects of, the more comfortable you're going to be in working with them over time. We'll talk a little bit more about this energy idea, the idea that the energy is conserved within one of these diagrams, and so we can look at things like convective available potential energy. And here we can, next lecture, talk about certain values such as the lifting condensation level, the equilibrium level, parcel path, and start to talk about some of these derived quantities that can be gleaned from a SKU-T. And so I'll end this lecture by asking you to look at page 5 of your handout, the idea of mandatory and significant levels. And so when we talk about mandatory levels, we're talking about certain pressure levels within the atmosphere where there's always going to be data reported, I should say, because our radiosondes here at Valpo are going to be taking data every 1 second of flight, which means that we would have an overabundance of data, and so we're going to really focus in on certain levels such as 500, 300, 700, 850. And you may think to yourself, these sound like some of the levels we've looked at when we've created upper level maps. And you're correct. We want our radiosondes to always report that data so we can compare one site to another and get an overall picture of what's going on in the upper levels of our atmosphere for the purposes of recognizing things such as forcing, ridges and troughs, and help to ingest this data into our numerical models. And so in your tasks, we are asking you to look a little bit at some of the data that you're going to work with in Python, but potentially work with some of it by plotting in a hand analysis sense. And so in particular, number 2, if you have access to a printer, I strongly encourage you to go ahead and print out a blank SKUT and plot the data by hand. If you choose to do so, please go ahead and upload this as part of your map journal should you wish to do that for extra credit. And this could be a great way to help you understand SKUTs and better understand what is working on, shall I say, behind the scenes in Python as you start to create some of these images. All right, that's all for now. We'll be back in a little bit with another video.